Welcome to the demonstration of the analysis of the classical loss sales model under periodic review. This classical model has been subject of research for quite some time, and one of the common knowledge is that finding the optimal policy is complicated because when you decide on the optimal policy, you have to keep track of all outstanding orders, and if lead times are long, this can imply also a huge state space, which basically means that computing the optimal policy, even storing the optimal policy, could be in principle impossible even under today's storage and retrieval and computation capabilities. Having said all this, recent research over the last 15 years has shown renewed interest in this important problem and also progress in terms of results. And based on this progress of results and also research that was done in my group at Eindhoven University of Technology on this loss sales model, I decided to develop a tool where it is easy to compare policies, in effect policies that have a special importance for the loss sales model. And by this comparison that you can do, you can get a good insight into the benefits of these policies, but also maybe somewhat striking results in terms of the properties of these policies. Now let me first explain the basics of the periodic review loss sales model without fixed order cost. This 100 represents the average demand per review period. This 100 below represents the standard deviation of demand per period. This represents the lead time, which is 4 periods. And here we have the holding cost per item on stock at the end of the period. And this is the penalty cost per item lost. And the objective of the research on the loss sales model has been to minimize the long run average cost. And what basically has happened over the last 15 years is that it has been proven that the so-called base stock policy, which implies that you order such that the sum of physical stock and outstanding orders is equal to a target value. In this case, you see the number 717. That's the way you decide on ordering. And for this policy, it is now known that if the penalty goes going to infinity, the base stock policy is optimal. It has been proven by researchers like Tim Huh. Then the fixed order quantity policy is completely different. That basically says, well, you order always the same quantity, in this case 83.53. And that policy turns out to be optimal when the lead time, this lead time gets very long. And this, the initial work on this was by Marty Ryman of Lucent Technologies. And then there's the so-called fixed non-stockout policy. The P3 is a classical notation for the non-stockout probability at an arbitrary point in time, or in this case at the end of an arbitrary review period. And this fixed P3 policy did not receive that much attention, although work in the 1990s by people in my group, Karel van Donselaar, Werner Rutten and myself, we basically developed not so much a fixed P3 policy, but a fixed P2 policy, which basically said try to order such that the fill rate at the moment that the order you place now is received, and then that at the end of that review period, that you always target the same value. Now, the fixed P3 policy basically says, when you determine your order quantity today, look at the period when this order quantity is received, and at the end of that period you would like to meet a target non-stockout probability. And it turns out that you can develop highly accurate approximations for this seemingly rather complicated expression that you have to solve then. And it turns out highly accurate and also fast in terms of computation. It's clearly not as fast as determining or executing a base stock policy or fixed order quantity, because for these two you have parameters and you know exactly what to do based on a very simple calculation. In the fixed P3 policy, every period you have to calculate a quantity such that the probability expression that involves multiple independent random variables and some complicated relations that needs to be computed, but with today's capabilities of computers, it turns out it's no big deal, and I will demonstrate this in the remainder of this demonstration. The tool is organized as follows. Here is a button which initiates a simulation-based optimization to compute the optimal policy parameters over here for both base stock policy and fixed order quantity policy and fixed non-stockout probability policy. So we can do this for this particular case. Let's tweak this instance a bit. We make the penalty cost slightly lower and the lead time slightly longer, and then we optimize parameters, and it takes a bit of time. Turns out the most of the time needed to optimize the parameters is taken by this fixed P3 policy. The other two policies, if you run this on a Core i7 of 4 years ago, which is basically the CPU I'm using at this moment, it's a kind of split second to determine this. But here you see then, if you do simulation based optimization and you do it for this fixed P3 policy, you basically, it takes more time. And here we find the optimal parameters. It's important to realize that I assume continuous demand. In fact, I assume gamma distributed demand with these mean and standard deviation. That also explains why you get non-integer numbers for base stock policies and order quantities. The accuracy of the procedure to calculate the fixed P3 policy is also represented here, because this is the target value that's optimal according to the simulation-based optimization, 0.819. But this is the outcome when you simulate with this value, and you see that these two numbers are quite close, which should be. Of course, for the other two policies, the outcome P3 is computed by the simulation under the optimal parameters. And basically, this is a basic simulation, so you can trust the numbers that are here. Basically, what you now can see that for these parameters, it turns out that the fixed P3 policy outperforms the other two in terms of cost. You see here the average inventories that is needed to accomplish this, and you see also the P3 values of the three policies, showing that the optimal P3 for the base stock policy and the fixed non-stockout probability policy are quite similar, whereas the fixed order quantity policy has a lower service level. Also an interesting byproduct, I must state explicitly, a byproduct of this experimental study, but quite consistently what you see here is that the order volatility of the base stock policy, being 0.92 coefficient of variation, basically coefficient variation is the quotient of the standard deviation of a random variable and the mean of the same random variable. And here the random variables are the replenishment orders, which are uncertain. And this is a long run expression or number. And you see that the order volatility, the replenishment order volatility, is quite close to the volatility of demand as the coefficient variation of demand is 100 over 100 is 1. And this is a quite typical result for base stock policy for lost sales when the service level is not too low. Fixed order quantity, of course, has no order volatility, but what you also see is that the fixed B3 policy has a remarkable low order volatility, while it still is a policy that responds to the state of the system in terms of the outstanding orders, but also in terms of the randomness of demand. It is, of course, you can do your own experimental study, but I just want to point out that using this tool and using, of course, more batch-oriented ways of running experiments, the outcome seems to be that in virtually all cases, this fixed non-stockout policy is outperforming the other two. And also shows all the time a serious implosion of volatility of replenishment orders in comparison to the volatility of the demand. And in particular, this reduction in volatility from 1 to 0.23 can be recognized as an inverse bullwhip effect. And it cannot be stressed enough that this outcome, which was also reported in the paper that we published on the fixed fill rate policy, there we saw the same phenomena occurring. And we believe that if you consider this lost sales model in the context of a multi-echelon supply chain, it basically implies that if the end items are controlled by a policy in the context of lost sales, if you then use the fixed B3 policy, you get a very low volatility upstream in the supply chain, which of course means that we will have much lower cost in the upstream supply chain than we would have under a base stock policy, for example. This needs, of course, to be further researched because the analysis of multi-echelon systems with lost sales is even more complicated than, of course, than the single item, single echelon setting that we study here, and already that has been basically a subject of research for over 50 years with not completely conclusive results. Okay, now let's turn to the rest of the capability of the tool by which you can experiment yourself. Here you see the three policies, one after the other, and the idea is that what we are going to do, we're going to simulate these three policies on the same demand process with the same initial inventory over time. In a way, you could say that the calculation of these parameters is running a simulation over a long time, say 100,000 periods, and then computing the policy results and adjusting it until you get the optimal policy. So that means multiple simulations, one after the other. In this case, we run a simulation and we provide some graphics of the evolution of inventory over time. The red line in the graph later on, and the green line gives the evolution of replenishment orders over time. And then we can check our long run average outcomes in terms of to what extent was this long run outcome also represented in terms of cost, inventory, service, by looking at a shorter horizon experiment. And of course, you can expect different discrepancies. But also we would like to see if you compare the policies under the same conditions, do we see still that some policy, and you would expect fixed non-stockout probability policy, that would it also perform better. Now we can do this by basically first doing an initiate experiment that basically initiates by setting a starting inventory and filling up all the outstanding orders basically by the mean demand. Of course, the longer the lead time, the more this initialization will have an impact on shorter term simulations. In this case we have a lead time of 6, so 6 outstanding orders. Basically we set the simulation length. Now we set it here to 200, and we can also influence the speed of the simulation. Now if we do a simulation speed of 10, we can start next to simulate, and here you see how over time we see it developing. And basically this implies now that we have run 200 periods. It's good. Now and then I've experienced that now and then the graphical representation stops while the under the hood the tool is still simulating. It will eventually stop with the right outcome in terms of the total simulation length. But now and then it could be that, let's say, the requirements on the CPU are of such as order of magnitude that one way or another it starts failing to update these pictures. In any case, what we now see is an outcome where we see 3 policies having, here you see the average cost more or less in line with what we have done, although we see that in all cases they're slightly higher. We do see the ranking that fixed the P3 policy, non-stockout probability policy, is still the best. We do see this implosion of volatility from 1 to 0.24, which is nice. And we can see that the fill rate, which is in this case not P3 but P2, is 80%, here 76, and here it's 80%. So here we see 2 comparable policies, and here is one policy that has a worse performance in terms of fill rate, has a higher cost, but has a lower inventory. Now, we can run the simulation for a longer period of time, so this could be amounting to something like 4 years. Now, you can say, well, whatever, why would I do 4 years? Well, we have to bear with uncertainty, so it's good to have an insight into that matter. But of course we can also decide to run it for a shorter time. So I initiate the experiment again and I simulate, and then we will be ready pretty fast, and then you see that of course the outcomes are different. And now we see that the volatility is not yet imploded like the 0.23. The highest service is by the fixed order quantity policy, so we see bigger discrepancies by coincidence and by the way these orders deal with the uncertainty, and apparently then we get the best performance but also the highest inventory. But on the other hand, if you look at cost, again we see fixed P3 is doing a better job at a very low order volatility than both base stock policy and fixed order quantity policy. There's one other option that is available, and that would be to basically, if you want to run step by step and see what really is happening, then you can look into by doing next period, and you see here, for example, these are the first orders proposed for the base stock policy. 49, close to 50, here 77, here's something in between. Need not always be like that. And then you see here, of course, always the same order. Here they all happen to be more or less similar, which is interesting. And so you can now, and here you see again substantial difference, in this case 55, 77, 90, 97. And this continues. You can see how order by order, and you can continue as long as you want, of course, but you do see order volatility already being quite different after 10 periods between the base stock policy and the fixed order fixed non-stockout probability policy. And of course this one's always 0. In this case you see high inventories, but also well, not so high service. So here seems to be in this particular case quite a discrepancy between cost, service. Of course here, because there's this service, there's high penalty cost. Inventory apparently is lower on average, but still not that much lower, but it has a serious impact. Of course, under uncertainty, think of this as in retail. you have lost sales, but you also have a multitude of items. So the key is to understand that you should use a policy that over this large range of items does a good job, which typically is rather well represented by just running for items a long run performance, because that gives a clue about the intrinsic capability of policies, because you run it over a long time, you meet all the kinds of uncertainties that might be there, and then you see, okay, that policy is doing a good job. And as I said, it seems to be that this fixed non-stockout probability policy is very robust. Now, I hope that this gave sufficient insight in the kind of experiments you can do. You can change all parameters. Of course, over here, if you run simulation, you have to put numbers here. You can also decide to put in your own numbers over here. That's up to you. And then you can hopefully understand, you can optimize parameters if you want to. And if you don't, you use the numbers over here, and then you initiate experiments and you can see what happens. That basically means that you could, for example, also put, for example, the base stock policy, put numbers in that follow from backorder models using some basic analytical models. Fixed order quantity, of course, is easy to do. Yeah, the fixed non-stockout probability policy you can put in numbers, but it's not always that clear what the right numbers are. Okay, success.